At sea, weapons tests are usually quiet events, controlled, sanitized. But this one was different. Because for the first time ever, Japan decided to show the world something no navy has dared to demonstrate in real ocean conditions. Actual railgun impact damage on a real ship. Not a lab test, not a simulation, a real vessel, real projectiles, real results. I'm Mike, and welcome back to Navy Network. Today, you're about to see why Japan's new railgun test may be the single most important development in naval firepower since the dawn of the guided missile. At the annual Defense Technology Symposium, Japan's Acquisition, Technology and Logistics Agency, ATLA, did something unexpected. They didn't just announce progress. They revealed the actual strike marks left behind when their prototype electromagnetic railgun fired hypervelocity, non-explosive projectiles at a moving ship at sea. And those impact patterns tell a story no PowerPoint slide ever could. Because unlike traditional naval guns, railguns don't rely on explosives, propellant, or arcane chemical timing. They rely on pure electromagnetic acceleration, firing a metal projectile at velocities so extreme, the ocean air itself becomes part of the challenge. And here's the twist. While the US Navy famously backed away from railgun development, shelving its multi-billion-dollar program in the early 2020s, Japan kept going, quietly, steadily, relentlessly. And now, their results suggest they may be closer to a deployable railgun than anyone expected, including the United States. What Japan finally revealed. For years, Japan tested its railgun quietly. Land trials, limited range shots, data gathering events with no public impact footage. Engineers talked in careful language. Officials avoided specifics. But at this year's symposium, that changed. ATLA unveiled something no nation had shown before: real-world impact marks from railgun projectiles hitting a real ship at sea. On screen, the images were clean but unmistakable. Dark burn marks, cross-shaped penetrations, clean puncture lines from fin-stabilized darts traveling faster than any naval gun round in existence. These weren't explosive hits, no shrapnel, no fragmentation, just raw kinetic energy punching through steel. For naval engineers, it was the exact confirmation they needed. The test took place aboard JS Asuka, a 6,200-ton experimental ship used as Japan's floating weapons laboratory. This vessel has one job: evaluate advanced naval systems in real maritime environments. Earlier satellite photos had already shown a large railgun mounted on Asuka's rear deck, an unusual sight that triggered speculation. But now, ATLA connected the dots. Not only did they fire the railgun at sea, they fired it at a moving target vessel being towed behind another ship. That detail matters. Hitting a moving maritime target with a hypervelocity projectile isn't just point and shoot. At several thousand meters per second, factors like barrel vibration, ship roll, electromagnetic stability, atmospheric drag, projectile fin alignment, all influence whether the round remains stable. And Japan didn't just hit the target. They hit it multiple times, consistently, predictably. With enough accuracy for ATLA to openly declare, this data will directly support Japan's path to an operational naval railgun. This wasn't a demonstration. It was a statement. A message to the world that railguns are not dead technology. They're evolving, and Japan is now leading the charge. Why railguns are so hard to build. To understand why Japan's progress matters, you first have to understand the weapon itself. A railgun sounds simple in theory. Two parallel rails, a massive electric current, a small metal projectile that rides a magnetic field to unbelievable speeds. No gunpowder, no explosive shell, just electromagnetic acceleration. But the engineering reality is brutal. Railguns are hungry for power, astronomically hungry. Every shot requires enough energy to power a small neighborhood for a moment. And then there's heat, unimaginable heat. When a projectile leaves the rails at 2,300 meters per second, the friction, electrical load, and mechanical stress combine into one devastating problem: barrel life. Most prototypes worldwide struggled to fire even a few dozen shots before rails warped, cracked, or melted outright. But Atla confirmed something extraordinary. Japan's latest prototype has survived over 200 rounds at around 2,300 meters per second. That's nearly double their earlier stated goal, and far beyond what most nations achieved. Even more impressive, Japan improved both round velocity and barrel life simultaneously. That means breakthroughs in metallurgy, cooling, and electromagnetic wear reduction, the exact problems that halted the US Navy's railgun program in the early 2020s. Meanwhile, JS Asuka's railgun testbed required 4 full shipping containers strapped onto the deck. One for power conversion, one for cooling, one for energy storage, one for control electronics. A reminder that this is still a prototype, a massive one. But Japan isn't shy about the challenge. They acknowledge openly that an operational naval railgun will require deep integration into a warship's hull. Heavy power systems below deck, reinforced structure, advanced thermal management, next-generation electrical plants. It's not a plug-and-play upgrade, it's a redesign of naval architecture. And Japan seems ready for exactly that. The test behind the test. While most eyes focused on the impact marks, ATLA quietly revealed something even more important. Japan didn't just fire the railgun horizontally at a moving ship. They also fired it at a 45-degree upward angle, collecting pure ballistic data. Arc height, velocity degradation, atmospheric drag, long-range projectile stability. This wasn't combat training. This was science, deep science. The kind of data you need when designing a naval weapon meant to operate across multiple mission profiles. To capture this information, JS Asuka carried a suite of custom instruments, a camera mounted directly under the barrel, a high-speed camera tracking projectile exit, a compact radar unit measuring velocity, deck sensors capturing vibration and shock, and even a drone recording from above, all of it feeding a massive analytical dataset. Exactly the dataset a nation needs if it wants to take a railgun from prototype to frontline combat capability. But the test didn't happen in a vacuum. Japan's railgun push sits inside a shifting strategic landscape. With China expanding its naval arsenal and developing hypersonic weapons, and North Korea continuing missile tests, Japan faces an evolving security environment where traditional defenses are being stretched thin. A railgun isn't just a futuristic toy. It is a potential counter to hypersonic threats, a long-range ship defense system, a low-cost alternative to missile interception, a weapon with massive magazine depth, a deterrence tool against swarms, drones, and fast missiles. And perhaps most importantly, it gives Japan a way to defend itself without relying solely on expensive interceptor missiles that can't be reloaded at sea. Railguns turn electricity into firepower, And as long as a ship has power, it has ammunition. That's why this test mattered. It wasn't about showing off a new weapon. It was about proving that a railgun can exist in the real world, on a real ship, under real conditions. And it worked. A global race revived. For decades, the United States led the world in railgun research. Billions invested. Years of testing. Thousands of engineers. And yet, after immense challenges with power, cooling, and barrel wear, the U.S. Navy's once promising railgun program was quietly shelved in the early 2020s. Not because railguns didn't work, but because the Navy couldn't yet fit them into real warships without major redesigns. Power systems weren't ready. Cooling loops weren't advanced enough. Structural stresses were enormous, and so the United States stepped away from the race. But Japan didn't. Quietly, steadily, they pushed forward. And now, Japan is showing results the United States never reached. Real, consistent railgun impacts on a real moving ship at sea. And here's what most people don't know. Japan has been talking to the United States about railgun research. A TLA officials confirmed they met with the U.S. Navy to exchange data, learn from America's earlier challenges, and incorporate proven research into Japan's effort. This isn't just a national project anymore. It's becoming the backbone of a broader international push. Japan has already formed partnerships with France, Germany, the Franco-German USL Railgun Research Institute. Meanwhile, other nations are watching closely. China publicly tested a prototype aboard a PLAN vessel in 2018, though its status remains unclear. Turkey has shown strong public interest. Germany has pursued electromagnetic launch systems for over a decade. France is working on next-generation hypervelocity projectiles. But only one nation has now fired a railgun at sea and shown real target damage to the world: Japan. And that puts them at the front of a race many believed was already over. A race not just for a weapon, but for a new class of naval firepower, one that might reshape how wars are fought at sea. The question is no longer, can a railgun work? Japan just demonstrated that. The question now is, who will be the first to put one on an operational warship? And Japan's answer seems clear. They intend to try. The future Japan just made real. The newly released data leaves no room for doubt. Railguns aren't dead. They're not outdated. They're not stuck in laboratories. Japan just proved they work. At sea, against moving targets, with repeatable results. And that changes everything. Because a working naval railgun isn't just another weapon, it's a shift in naval doctrine. A shift from chemical propellant to pure electricity, explosive warheads to kinetic slugs, limited missile magazines to near-endless firepower, multi-million-dollar interceptors to low-cost hypervelocity shots. And for a nation like Japan, surrounded by rising missile threats, narrow sea lanes, and growing regional tension, a weapon like this isn't just an experiment, it's a necessity. A TLA officials admit there are still enormous challenges ahead. Integrating massive power systems inside real warships, designing new cooling loops, reinforcing hull structures, storing and handling electromagnetic projectiles, coordinating fire control at extreme velocities. This is years of engineering work. But the tone from Tokyo was unmistakable. They're committed. Because Japan isn't trying to build a science fiction weapon. They're building a solution, a long-range, high-velocity defense system designed for a world where hypersonic threats are becoming the norm. And maybe that's why this moment feels historic. For the first time, the world isn't looking at simulations or prototypes firing into sandbanks. We're looking at real impacts on real steel, caused by a weapon that may soon redefine naval warfare. So let me leave you with this. If these tests continue to succeed, and Japan mounts a railgun on an operational warship, they won't just be reviving an abandoned technology, they'll be rewriting the future of naval firepower. And the US Navy, once the leader in this space, might one day look to Japan for the blueprint on how to finish what America started. If you support the sailors, engineers, and innovators pushing the boundaries of naval defense every day, drop one word in the comments: respect.